Okay, so if you guys remember, each time we do this, we try to highlight a new option for self-starts. So this is one called Visual Patterns, and I did not create these. These were like already pre-made from the website. So this is an upper-level question. So I'd like you guys to just take a second and see if you can kind of figure out how you would do this. The students see this image here of the 3 different, what they call steps, and it's a pattern. And you just simply ask how many cubes would be in step 43. And again, depending on the level, what would the equation be? So they can figure it out actually with concrete materials, or they can just do it on pencil paper. So I'll give you a second just to play around and see if you have the answer to that. All right, so if we were to actually look at this answer, if you just did simply cubes in step 43, you would have 88 cubes. And for those, Mark, who was trying to create the equation, you would have y equals 2x plus 2. Y equals 2x plus 2. So the amount that you have, you double it, and then you add 2. So then you could jump right to step 43. Again, they can also just build it and then just create step 43. Here are some other adaptations for the younger grades. Here's a new pattern. Again, I did not create this. This is just one of them that's available. So, oh, I'm pushing the wrong, sorry. There we go. Maybe, there we go. Okay, so here's some suggested adaptations just for the younger grades. You could ask them things like how many puppies will be in step blank, depending on how far you want them to go. What is the pattern? Or let's skip count to step whatever. Create a line graph to show the changes over time from one step to the next step. So there's lots of ways that you could use this, even if you don't do the step 43, what's the equation, okay? So they are designed, this Visual Patterns website is designed to calculate the total number of for step 43 at each time. Go ahead. And then create the equation, but again, you can adapt it any way you want. Here's just an example. It's just a screenshot of the Visual Pattern website, which will be on the Padlet again for you guys. You could just see, and this is not even the whole screen, and there's a whole bunch at the very top. It looks like there's about 380 different options, just different kinds of pictures you could use. So we just wanted to kind of showcase that for you.
Okay, now that we're done with our warm-up, I'm going to talk about how good mathematicians do math. What do good mathematicians actually do? What are the things that we want to teach our students to do so that as they're learning mathematics, they are becoming those good mathematicians? Anybody have any ideas on that? Okay. Problem solving. Understanding the question. They're the 8 standards for mathematical practice, the same 8 standards that all of us have in every single grade level from K through 12. We have our 8 standards for mathematical practice, and I don't know about you guys, but my first year teaching, when I opened up that standards document, I scrolled past those. I'm like, no, let's get to the real stuff I have to teach. And it was only until a couple years later that I actually figured out just how important they were, because this is how good mathematicians do math, and we want our students to be those good mathematicians. So there they all are. We'll go over them in detail, so I'm not going to spend time reading them all out right now, but there are 8 of them. And we start with, I think the first one is pretty obvious what it means. Make sense of problems and persevere in solving them. We can't solve problems until we know what we're actually really trying to do. And so we really need to be able to make sense of that. Our problem-solving strategies, which we will be addressing a little bit later, are going to come into play on that. But the second one is perseverance. There's actually some studies that show, I can't remember when the study took place, but Twilla High School participated in it 2 years ago. But what it is it talks about the perseverance in students at high school level. And in Japan, those students will work on a problem until it's done. In the United States, less than 60 seconds before they give up. And so we really need to instill that perseverance, that we don't stop because it's hard, we stop because it's done. What does that look like in our classroom? It's mathematical discourse. and modeling self-talk, which we actually did talk about in a couple lessons ago, that math talk, but also teaching our students to self-talk. And I had an epiphany this year too as I was doing a Zoom session. Like, my students are struggling, and I don't know why they're struggling, because I say stuff all the time, but they don't know that the stuff I say when I'm solving a problem is the same stuff that they need to say to themselves. And so I want to get better this year at actually making them, like, I'll say, or I'll ask a question, and then I want them to repeat the question back to me so that they get in the habit of actually asking themselves those questions. Where is the variable? What is happening to the variable? Those are questions that they should ask themselves, not just what I ask because I'm a teacher. The problem-solving strategies, which we'll talk about again later, using multi-step problems. We need to use multi-step problems in our class because that's what teaches that perseverance. But we also need to make sure, and this is all part of the make sense of problems, make sure that when it's a multi-step problem, you stop. Have we answered the question yet? Remember, what was the question really asking us for? Have we answered that question yet? Does what we have actually make sense? And now is one of my favorite math practices, and it's one of my students' favorite math practices, Math Practice 2. Before I talk about that, I want to first, you see this image up on the screen, and I know it's not as good a quality with the lighting that we have, but what are some words that we could use to describe what you see without saying, there's a bunch of umbrellas hanging in the air? What are some things that could describe what you're seeing? Colorful. What else? Floaty. How does it make you feel when you see it? Happy, bright. So those are some things that we can say to describe this. And I want you guys to practice that as I move on to some new pictures. I want you guys to be able to explain what you're seeing without saying exactly what it is. So first, we're going to count off 1 and 2. So we're going to separate you guys into groups. We're not moving or anything, but I want you guys to count off 1 and 2. We'll start over here with Miss Knudsen. Don't forget your number. Now here's the rules. No talking until I give permission. You're going to be tempted to say some things. Please avoid that temptation. Now, number ones, you are closing your eyes right now. No peeking. If you count it off and you are a number 1, you are closing your eyes. Number 2, your eyes are open. Get ready to see and absorb and take it all in, but don't say anything. She's turning off the lights. She's rescuing us. There we go. Okay, now, number 1's open your eyes. Remember, you should still not be talking right now. And number 2's, you are now going to close your eyes. Please keep them closed. No peeking. Number 2's. All right, open your eyes, everybody. Now, I'm going to ask you guys to share some words that describe what you saw without explicitly stating what you saw. Well, let's start with number 1's. Where are my number 1's? Raise your hand. Okay, call out what you saw. Nighttime. Okay, number 2's, think about that word. Does that describe what you saw? Okay, number 1's, share something else. Huh? The moon, okay. Does that share, or does that explain what you saw, number 2's? Number 1's, anything else? How did you feel when you saw it? Blue, random? Swirly, okay. Okay, now let's switch to the number 2's. Call out some things that you saw, number 2's. Number 1's, does that describe what you saw? Peaceful. Does that describe what you saw? Okay, so now, did I trick you guys? Did I show you the same image and just make you close your eyes for nothing? It feels like it. Are they the same? Sort of, right? Yeah, we see starry night, we see stars, we see the galaxy in both pictures, we see beautiful stars, we see a tree in the foreground, we see mountains and bushes and stuff in the background. Okay, so this is the difference between quantitative and abstract. Both of them have their time, their purpose, both of them are beautiful in their own ways. And just like mathematics, we have our quantitative and we have our abstract. And I always like to tie back to this. The quantitative is the real life. The abstract is the abstracted version of that we use, but it still is very, very useful and beautiful in its own way. So math practice 2 is reason abstractly and quantitatively. Abstract means we're using symbols like numbers, operations in an expression, graphs, even other math models. That is an abstract reasoning. Quantitative means we can relate our abstract models back to the problem that we're actually really trying to solve. And it really is a tough skill to help our students develop. So what does it look like? After solving a problem, we use the units of measure. And Janine is also going to be talking about this. It's not just 3 plus 4 is 7, it's 7 cats. We always ask, what does that mean? Always ask for those units of measure to tie it back into the quantitative. And my students now, and there's times where I forget, and I say x equals 7, and they're like, 7 what, Mrs. Proctor? We have to make it quantitative again. And so that's pretty exciting. Abstract reasoning is how we do the math, but quantitative is why we do the math. Math practice 3 is construct viable arguments and critique the reasoning of others. This is also one of my favorite ones because students sometimes feel like they don't need to show their work. It's not that important. But math practice 3, good mathematicians will always show their work or at least be able to explain their reasoning. Sometimes that looks like actual work on a paper, solving out an equation. Sometimes it's writing a sentence. I believe this because, but we have to construct those viable arguments. Last training, I did the My Favorite No warm-up, and that's a great way for students to, critique, yeah, that's the word, critique the reasoning of others. Because they have to find the mistake, they have to encourage that student to do better, explain what their mistake was, and so that My Favorite No is one of the first warm-ups I do so that they can see that math practice 3 in action. Critiquing the reasoning of others, we have to be careful with that word critique, especially in those younger grades. They need to know that it's a positive, it's constructive criticism, but it's not always just saying this is wrong. Sometimes it's just looking at it to say, yeah, that's right, I agree with that.
I just want to remind you guys on the My Favorite No that you always address the positives first. You always say, okay, only tell us what was done correctly. Then after everybody's exhausted their ideas, then you say, what could they have done better? What little mistake did they maybe make that you can learn from? So be really careful the way you word that, so always stay positive, but always start with the good things first.
Sometimes the only positive thing is at least they showed their work. But that way we can see because they constructed their own viable argument, allowing us to be able to critique that. So what does it look like in the classroom? It's talking about math. Ask the questions why or how do you know every single time. I don't ever just accept x equals 7. Why? Why does x equal 7? Because, and then they can explain that process again. Make showing work or showing thought processes the standard, not the exception. Maybe you guys do, and maybe by 7th grade they think that they can get away with it, but I still have those 7th graders thinking that they can turn in a page with just the answers, and it makes me so crazy because I know you guys don't do that. So we really just need to make sure that they understand that this is a standard and it's never going away ever. And incorporate that error analysis like we did in the My Favorite No. Math practice 4 is a really easy, obvious one, model with mathematics. It really is closely related to math practice 2 because we have these real life problems that we need to solve, but we need to help students understand that when you have a real life problem, you can tie it into math and you can use those abstract math models to actually solve the equation. But also make sure your students know what kind of models are available to them. It's math tools, it's algebra tiles, it's your base 10 blocks, it's your counters, it's all sorts of things in addition to graphs and tables and equations and all sorts of stuff. So make sure that the students know what models are available to them and have them solve the same problem using multiple models. Have them do the counters, then have them do it abstractly with just expressions and equations.
There's actually a lot of research that says you need to do that all in one moment. So it's not that one day you do the problem using a model and then the next day you just do it, just a normal algorithm. You do them together multiple ways at that same moment, if that makes sense. So they see it in all different ways, and they don't just think, oh, this is the time to do models, and now it's just this time to do it this way or that way. Hopefully that makes sense.
Okay, math practice 5, use appropriate tools strategically. Again, I always start off every single year, the first 2 weeks, this is all we do is we talk about the math practices. And it really helps because it helps form our culture and it helps form our classroom norms. One of which is use appropriate tools for the appropriate job, because students later on, when they get their compasses and they have a point, they need to know that the appropriate use is to put it on the paper and draw a circle, not poke their classmates. And because we had that discussion early on in the year, then it makes sense later on when I really try to enforce that. And even just rulers, they think that they're really fun helicopter and whirring sounds. And so we have to really have that firm conversation that there's appropriate tools for math jobs, and there are fun other ways we have to use them for math, in addition to other things that apply. Yes, Heidi?
I always tell my kids when I hand out manipulative kids, I'm like, what are these? They're like, they're tools. What are they not? Totally. Because it's so, yeah.
Yes.
I get out the base 10 blocks and we start building, and I'm like, what are these? Tools. What are they not?
Perfect. Perfect. Math practice 5 right there.
Set a timer for like 30 seconds. Play. Done.
I also think it's important to just list all of the tools that we have available. Sometimes there's tools that we don't realize. They think, oh, math tools, that means calculator. Your fingers can be a math tool. Paper and pencil can be a math tool. Even ripping up the paper to create your own sort of manipulative. There's so many things available to you. You just need to make sure that the students really actually know that. So encourage the use of the math tools, especially now that I have the 7th graders. I tell them, use your calculator. Stop with the fingers at this point. Just plug it into your calculator. I don't have time for you to do this. 72. It's so much faster to just type it into your calculator at this point. So use the tools. Now math practice 6. Who knows math practice 6? Good. I didn't state it because I don't want it to give it away. So here's math practice 6. Here's the activity. Nope, you're not even close, but that's okay. I appreciate the attempt. Okay. Here's an exercise for you. What shape belongs in the space? Can you guys see the image, or do we need to lower the lights again? We're good? Okay, what shape belongs in the space? Square? A green square. Good. Oh, color. Look, I like it a lot. I actually didn't do green, I did red. Okay, a square. Square is wrong. Pratt had it. Why is square wrong? Look at the shapes that I had before. I had a 3-sided figure. What's a 3-sided figure called? A triangle. I have a 5-sided figure. What's a 5-sided figure called? A pentagon. And a 6-sided figure is called a? So I'm missing a 4-sided figure. What is the name of a 4-sided figure? Are squares also quadrilaterals? Yes, but that's not the shape that's missing. All right, I tricked you the first time. Now you guys will be just fine. What shape belongs in the space now? You guys know what those symbols mean? Those lines mean that all of the lines are congruent, right? So now it's a square, obviously. No. I got you again, it's rhombus. Good job. We don't know anything about the angles. All we know is the side lengths are congruent. Now, for a triangle, all sides being congruent also happens to mean that all angles are congruent, so it is an equilateral triangle. However, we don't have that same property with our higher order figures. So it's actually an equilateral pentagon, an equilateral hexagon, and a rhombus. All right, I'm really done tricking you now. Now we have equal side lengths, and we have all measures congruent, or all angle measures congruent. So what is the shape now? We finally made it to square. Yeah. Because all of those properties that make a square are there. So, before I tell you what that math practice is, let's do one more exercise. Can you guys see that one okay too? Discuss with those around you, if you can do so safely and distantly, what's the issue with the work? We have on the screen 30 plus 60 equals 90, plus 4 equals 94, plus 7 equals 101. What's the issue? Is there an issue, or is it perfectly fine?
There shouldn't be more than one equal.
Yeah.
Yeah, like every section should be equal to all of the sections.
Yeah.
Exactly.
30 plus 60 does not equal 90 plus 4.
But 30 plus 60 equals 90, so it's fine, right?
No.
But it does not equal 90 plus 4.
I have middle schoolers who are still making this mistake because they're lazy. Thankfully, they're showing their work, so I have to give them points for that. But we still need to expect Precision. Oh, yes. Kids are definitely doing that. Done. I will send them to your room. That will be a fun day for me. Math practice 6 is attend to precision. That's the one. So attend to precision. We have to be precise in our definitions. We have to have that precise understanding, and we have to expect that of our students. Because precision doesn't just mean completely 100% right all the time. Accuracy is nice and it's great, but precision really refers to clarity and correctness. And it's that clarity that we're after in this precision. It doesn't always mean we have to solve problems in a certain way. We can solve them in a variety of ways as long as we're being precise in those ways. So what does it look like in the classroom? We need to make sure we're taking care with arithmetic, obviously. I would say that probably 90% of the mistakes that I have in middle school are with negatives because they lose the negative somewhere along the line. It's that precision, and so that precision is really helpful. Proper use of symbols, like that equal sign. The equal sign is really, really important. We need to make sure that we are using it correctly. And this is a non-example, so please understand that. That is a non-example. Expect proper use of vocabulary and teach the correct definitions. Just like the other example I gave, in 2 dimensions, what is a 3-sided figure called? So then what is a 4-sided figure called? And it's not a square. A square is a quadrilateral, but quadrilateral is the proper name for a 4-sided figure. Okay, math practice 7. Look for and make, yes, Mark.
We'll get to that.
Regrouping, breaking apart. I mean, does it matter that we're teaching them synonyms for the same things?
Yes, I would reword it over and over in many different ways, like in the same conversation. And that way it's also a way to accommodate for our special ed students who may not understand one thing but maybe understand it another. I always put in the correct terminology and then I give the more layman way to say it, but then go back to ending with the correct terminology. And then I would also really look at those Greek and Latin roots. For instance, quadrilateral, take out the quad. And what does lateral actually mean? And, really, and then that way when they see those, they start connecting that quad, quarters, quad, quadrilateral, your ATV. Just really making those connections, and it's just going to make it so that it makes more sense to them. And then they're going to remember it better. But I would just say it a couple different ways. Yeah.
And that precision of language definitely comes a little bit later too. When you're first doing a hands-on exploration, it's okay if they're saying things like, no, I'm just going to take it away from this one and move it over here. That's perfectly acceptable. But after we have that hands-on exploration and they're starting to discover these properties for themselves, that's when we say, okay, remember that thing that we did? This is the right way to call it.
And maybe even put up a chart for the younger grades, the taking away. What do we say in math? We call it this. So use their term and translate it to your term so that they can refer to that all year long.
And we will also talk about this one later too, but that equal sign too. I almost never say is equal to. I say is equal to and balanced with. Is equal to and the same as. That way they know that we're saying the same thing multiple ways and they have the same meaning that we can use interchangeably. So math practice 7, look for and make use of structure. This one and math practice 8 are very, very similar. The difference is in the structure. Math practice 7, we're looking for patterns and realizing the significance of them. I usually do a big, long example with my students that goes something like this. We know that 2 plus 7 is equal to 9, right? And so if 2 plus 7 is equal to 9, it's pretty clear that 2 cats plus 7 more cats is going to be equal to 9 cats. That's easy. It's obvious. So then what about 200 plus 700? What is that going to be? 900. They're utilizing the same units, and we make sense of the fact that we have to keep those units the same because it's the structure of the mathematics. And so then when we teach fractions, all we have to do is go through this and say, okay, well, if 200 plus 900, or 200 plus 700 is 900, then 2 tenths plus 7 tenths is going to be 9 tenths, and they'll know that it's tenths and not 20ths. They'll know not to add the denominator because they see that structure, that we're just adding like units and keeping those units the same. Structure is also things like we can see the structure of 1,364 is expanded form. 1,000 plus a 300 plus a 60 plus a 4. That's the structure of the mathematics. So what does it look like in the classroom? It's students catching onto the students are already going to catch onto those patterns naturally. We just have to help capitalize on it and then say, no, that's a really big deal. That's significant. Let's talk about that more. And we can see complicated multi-step problems as a composition of smaller, more manageable problems. I actually have a 10th grade level problem that I gave it to my 6th grade students last year when we talk about this math practice, because it's just multiple steps. So you might have this big long square root of x minus 7 plus 2 equals 20, but all you really need to know is that something plus 2 is 20, and you can start using that structure to back it down. And the last math practice is math practice 8. Look for an express regularity in repeated reasoning. Again, our students are naturally going to be doing these kinds of things. We look for generalizations and shortcuts. We make assumptions based on patterns, and we reuse strategies and methods on similar problems. So in a classroom, it's going to look like students finding that shortcut for long division, and we talked about this with our 4th and 5th grade teachers, where we did our long division with our hands-on manipulatives, and we slowly worked towards that algorithm. That's that repeated reasoning. Fraction division, the patterns that we see in fraction division. Powers of 10, 10 times 10, we end up moving the decimal place, and we see that extra 0, and the students are going to catch on to those. And the multiples of 9, the patterns that we see with the multiples of 9. We reuse the strategies and methods from similar problems. When we get to a new problem, we say, hey, doesn't that look really similar to that other one? What strategies worked for us there? So now we're done with our math practices, and we're really close to break time, guys, so just hang in there. We're just going to review our last couple of trainings so that we can tie all of this in together and see where it all ends. August. Remember, that was when we watched that Sherlock Holmes video, and we talked about doing math, actually developing the mathematical ideas, avoiding teaching the methods first. We don't want them to know the algorithm first. We want them to play with it first. Focusing on concepts rather than the rules. Filling our brain attic and hard drive with things that are really useful. Discover the mathematics, theorems, and algorithms, and inspire learning through surprise. And we talked about how we do this is we actually play with mathematics.
Keep books closed.
Yes, which led perfectly into our September training. Okay, how do we play? We look in the book for ideas. We don't teach from the books, we look in the book for ideas. We tell stories. We get out those manipulatives and we play. We play in the small groups. After we play, and this is where it all really has to come together, we can't skip this part. We have to discuss, we have to summarize, we have to finalize all of the things that we just played with. And that's where we formalize that vocabulary, which is that math practice 6, where we start developing that precision of the definitions. Then we had October and November, where we actually did get to play with the math. In our math camp, we had a lot of really fun activities where students got to see math in ways that they normally don't get to see it, and we really got to experience playing with math. And then we had our January. That was our last training. We had some crazy time since then. January focused on math talk, talking in the classroom, that mathematical discourse, starting with problem solving, utilizing that error analysis as math talks, constructing arguments, noticing, do you see those math practices hidden in all of those ones? Debates. And then we talked about the problem solving strategies that we recommend, and what we recommend first and foremost, stop using keywords. Those keywords, as we saw in that video of that girl who saw one particular word and she used it inappropriately and ended up adding when it was supposed to be subtraction. And then we have our 3-read strategy, reading it 3 times, making it real, acting it out, summarizing it. All of those are really great problem-solving strategies. So now it leads to this, and I know, will you turn off the lights for this one? I know you guys won't be able to read it, but this is actually the coherence map that Liz sent out a couple times ago. I don't even know. Weeks? A week? 2 weeks? Whenever you sent it. It was awesome. I chose one of my standards, of course, because Math 7 is important to me. So I chose one of my math standards. That's the one that's got the little like map location pin right there. But you can see all of the standards that come before. There's a lot of 6th, 5th. It goes all the way back to 4th. But also, if they don't get those standards and they don't get my standard, then it goes all the way up to high school math. So does it matter what the younger grades do? Does it matter what I do for their long-term success? And we have to recognize that connection. We have to recognize that lateral movement and how important all of these things are altogether. That particular standard is use variables to represent quantities in the real-world problems and construct simple equations and inequalities to solve problems by reasoning about quantities. Did you know, 4th grade, that mattered? What you teach in 4th grade has a direct influence on equations? Of course, you're like, well, it's so far down the road, it doesn't matter, right? I know you don't think that. Okay, so what's the point? What's the point in all of this? Why did I go over the 8 math practices? Why did we talk about all the things we've done for the last year? Cliffhanger. it's time for a break.
Pee and get the answer.
So we'll just we are actually running a little bit ahead of schedule. So 10 minute?
10 You guys have earned
10-minute break. And if you want to return with your office chairs because those bleachers just aren't cutting it for you, I get it.